Mr. Taru. In this video, we are going to introduce a lot of vocabulary and basic formulas dealing with circles, like diameter, radius, circumference, area. And then when we get all this sort of formality done of introducing circles, we are going to be doing probably 4 or 5 examples of dealing with naming arcs around a circle and finding arc lengths around a circle. So I don't do just example videos, I do full lessons, and this is my class's first lesson on circles. So let's get through the vocab first. A circle is a set of all points on a plane which are equidistant from a given point, which we're going to call that a center. Now I do need to say, and I didn't write it in my definition, but these are points on a plane. If it was a 3-dimensional object, we'd be defining a sphere. So this constant distance is the radius. So when we look at the diameter or the diagram of a circle, from the distance between center to the actual circle itself is going to be called the radius. The radius is a segment with one endpoint on the center of our circle and the other endpoint on the circle itself. And as we rotate this, as you would with a compass, to draw a perfect circle as I did here, that constant radius or that constant length of the segment is the radius. Now if you take that radius and you run it not just to the center but all the way through the center to the opposite side, that's going to be the diameter of the circle. So we have, and its endpoints are both going to be on the circle itself. So we have the diameter, and then because the radius only goes to the center and not all the way through the circle, the radius is always going to be half of the diameter. Congruent circles, the only thing you have to measure with a circle is that radius. So congruent circles are simply 2 circles that have the same radius, or radii. And then we talk about, not going to deal with them too much in this particular video, but to get all the vocab out of the way for the rest of our videos dealing with circles, or in my geometry class, the rest of our chapter, we have a central angle. A central angle is an angle whose vertex is on the center of the circle and, goes through the circle itself. An inscribed angle, and I'll look at my picture here in a second, an inscribed angle, which I should have highlighted, since that's what this is the definition of. An inscribed angle has the vertex on the circle itself, not on the center of the circle, and its measure is equal to half the degree of the arc. I guess I probably should have kept reading this. A central angle, I did write them, but the vertex is on the center of the circle and its measure is equal to the degree of the arc. So I've got a circle here and I've got a central angle. I know this is a central angle because I've placed its vertex on the center of my circle. And if I've indicated this as this arc here being from, well, I guess call this A and B, this arc measure is going to be 40 degrees. So the central angle is going to be 40 degrees as well. This will be helpful in upcoming sections when we start finding things like sector area and segment area. Now, if I draw this orange angle here with its vertex on the circle, its measure is going to be half of the arc. So this is a 40-degree arc. That means that this is going to be a 20-degree angle. Now, I've kind of, I didn't want to go straight through the circle because it doesn't really matter where this vertex is. If I draw an angle, any angle, no matter where I place it, if I place the vertex of the angle on the circle and then go, and match up this arc here, and again, hitting sort of like the endpoints, if you will, of this arc, kind of missed a little bit there, that arc is 40 degrees. This angle's vertex is on the circle. This is an inscribed angle. Its measure is going to be 20. You put the vertex here, its angle is still going to be 20. You put the vertex here, its measure is still going to be 20. And if I make any more angles, I'm going to have a mess of a diagram. So no matter where the vertex of your angle is, if the vertex, well, assuming, of course it's on the circle, no matter where the vertex is on the circle, the measure of that inscribed angle is going to be 20 degrees. Even if you get really, really close here, it's still going to be 20 degrees. Half of the arc, the measure of the arc, or the arc angle. Arc addition postulate. This is kind of the same as a segment. This is basically the same as the segment addition postulate, only with the segment addition postulate that we learned way early in geometry now. you know, instead of our lengths being straight that we're putting together, they're going to be curved. So arc addition postulate, the measure of the arc formed by two adjacent arcs. Just like with your segment addition postulate, you know, we put them together. If I have a segment of 2 and a segment of 5, and you put them together, you have a segment that's 7 units long. And that would be the phone. Be right back. Okay. So, now of course, I guess I need to kind of correct myself a little bit. I was starting to talk about the segment addition postulate as in terms of lengths. This is the measure of the arcs, which is going to be in degrees, but the lengths actually add up themselves as well. So if we have, I've kind of made this look like 180 degrees. So if this arc is, let's say, 60 degrees, and this adjacent arc is 120 degrees, then 60 and 120 is going to be 180 degrees. And though this notation is dealing with the actual, you know, like number of the degrees of the arc, the length, of course, would be the same as well. If this is a length of 2 and this is a length of 7, then this entire arc has a length of, what did I just say, 2 and 7? Then the entire arc is going to have a length of 9, if that's what I said. 2 and 7 adds up to 9. So those adjacent arcs, the overall measure of the arc together is just going to be simply added together. Now, before I move on, this is the measure of arc ABC. I'm trying to indicate what direction I want to go in. You know, if this is, if I hadn't made that so darn straight, but I wanted to talk about diameter, you know, if I just say arc AC, you know, do I want to go this way or do I want to go this way? Well, if I specifically need to rotate around the circle, and you normally will, name an arc, you know, on one particular side, we do want to include that additional angle in there. Like, and this could be, I guess I could move C over here and say that the measure of arc AB plus the measure of arc BC is equal to the measure of arc ABC, but still include that middle point to make sure that your teacher or you know what part of the circle you're talking about, not just wanting to wrap around the other direction. All right, so let's get to our, actually not example, but I've got a couple more definitions here before we get to our first example. Coming right up. Next page of notes. A minor arc, it has a measure of 180 degrees, and we generally do name that with just 2 variables, unless you want to include that third variable if you're doing the arc addition postulate. A major arc is wrapping around the circle, and you're wrapping around it more than 180 degrees, and we always want to name that with 3 variables. So if I look at my diagram here, well, never mind, I'm going to get ahead of myself. I got plenty of examples to do. So just make sure you name your major arcs with 3 variables. And a semicircle, of course, equals 180 degrees. This arc will, basically, you could say, starts and ends at the end points of your diameter. Concentric circles are circles that are coplanar and have the same center. That's pretty easy. You'll have to think of as like a bullseye. And all those circles have the same center, which is I guess the absolute center is the bullseye of the target. We have a couple of formulas. Some of these we'll use in this video, some of them we'll use in the upcoming videos, but we have the area of a circle is pi times the radius squared. We have the circumference, which is the distance around a circle, is 2 times pi times r, the radius, or 2 times the radius is just the diameter, which is going to be diameter pi. Now don't forget, pi is this value, rounded off, is 3.14, and pi, that ratio, that 3.14 comes from, it's the number of diameters of a circle it takes to get all the way around. So no matter how big or small your circle is, if it's a perfect circle, it takes 3.14 diameters to get all the way around that circle. Arc length, which is what our examples are mainly going to be focused on once we start here, is equal to the measure, and we're talking about a degree measure, the measure of arc AB over 360 times 2 pi r. It's arc length. So really all we're doing is finding the circumference of our circle, the distance all the way around it, and then just simply multiplying it by what percent of the circle are we interested in or wanting to highlight. You know, the measure of this arc AB is over 360. That's the entire rotation of the entire one rotation that makes a circle. So you're simply just doing part over whole. It's just the percent of the circle you're dealing with times the circumference. So I got a lot of parts of this to this first example, of which there are 4, unless you want to count each of these separate. I don't know how many examples I'm doing. At any rate, let's see here, pick up some yellow chalk. I want to name all the minor arcs, all the arcs that I can come up with that have a measure of less than 180 degrees. And with these kind of questions, you want to be very organized in how you do this. So I'm going to start here with A. Now, I'm going to wrap clockwise just to make sure I don't forget any. So we have arc AB. We have arc, we have BC, but trying to keep it as organized as I can. 180 plus 50 is 130, so that's less than 180. So we have arc AC. And if I keep wrapping around, I start to go over 180 degrees. So then we have BC. If I go from B to D, that's not going to be a minor arc because it's not less than 180. It is 180 degrees, so we're done there. Pick up here, we have from C to D. And finally we have the arc, I can't wrap around all the way to A, that's more than 180 degrees. And we have arc DA. So around this one circle with the 1, 2, 3, 4 points that I have on this particular one, and I just want to scan to make sure that I haven't missed any. Yes, we have 5 minor arcs. Now as far as the major arcs, arcs that are over 180 degrees, let's go ahead and start here with A again. Now I got from A, this is less than 180, this is less than 180, but if I wrap all the way around to D, that's more than 180 degrees. So I can either call this arc ABD, or I can call this arc ACD, but that still starts and ends at the same point. So I'm going to just pick one of those two names. I'm not sure if your teacher's going to count those as 2 separate ones. I don't believe I did. No. So AB, I'm going to go ABD. And if I wrap all the way around, well, that's just the complete circle. So that arc is the whole circle. I'm not going to count that. So I got A, B, all right, so let's try here. B, C, D, again, is 180 degrees. That's not major. It's got to be greater than. So how about B, C, A? And I could name that as B, D, A, but that's really that's just another name for the same arc. Again, you know, if your teacher wants each one of those, include them all. I'm just going to use that one. So B, C, and then A again, or B, D, A. Now let's start with C. C to D is less than 180, but C, D, A is another major arc. Starting to hope I don't run out of room. C, D, B. And if there's another answer, I'm officially out of room. Let's see here. C, D, B. All right. Now I'm going to come over here to, and I don't want to wrap all the way around again. So I'm going to start at D. We have D. How about DAC or DBC? And I don't have that yet, right? D ending start. I'm looking for an arc name that either starts and ends with D and C, and I don't have that yet. So I do need to include one more. D. How about we go DAC? And again, I can call that DBC, but I'm describing the same arc, and then I'm back to A. So I think that's my 5 answers, and that's what I have in my notes. Awesome. Semicircle. Now a semicircle is again, you're only rotating around halfway, 180 degrees. That's why I omitted those 180 degree answers, because that's a semicircle. So we have DAB. Or, and I still need to include the 3 letters, even though I said that, we basically use 3 letters when we're talking about major arcs. I should have made that notation here as well as far as a semicircle. Do I want to wrap around to the left, if you will, or to the right? So it's either DAB or it's DCB. Great. Now what's the measure of arc AB? Anytime you see me put a little M in front of my arc, I'm looking for a degree measure, not a length. So the measure of arc AB, well, the central angle is equal to 80, and the measure of the arc is equal to the central angle. So the measure of arc AB is going to be 80 as well. The measure of angle AEB, I'm not sure exactly why I guess whatever, it's already in the diagram, so it's 80 degrees as well. Actually, I know I included in my notes. I'm just trying to highlight again that the central angle is going to be equal to the measure of a central angle is going to be equal to the measure of your arc. If I had, again, an inscribed angle, then that would be equal to half the measure of the arc, which would be 40 degrees. If I hadn't, if I say it went from A to just some number out here like AFB would be 40 degrees, half of 80. The measure of arc AC, well, AC, now, see, the arc of AC is made up of two pieces, the measure of arc AB, which is 80, and the measure of arc BC, which is equal to 50. So the measure of arc AC, which is made up of two parts, is simply going to add them. So we have 80 plus 50, which is equal to 130 degrees. We have the measure of arc DC. Now this is the only unknown arc that we have out of total 360 degrees. So it's just going to be 360 minus 100 minus 80 minus 50. And let's see here, 360, 260, 200, 180, and 180 minus 50 is 130 degrees. And then we have the measure of angle DEC. Well, if the arc is again equal to 130 degrees, then the central angle is going to be the same. It's going to be 130 degrees. Okay, since I did that in my head, let me just make sure I did not make any mistakes. Now, I want to highlight this, and we're going to find the measure, or excuse me, not the measure, but the length of arc DC. This is my first example for arc length. Well, arc length is equal to what percent of the circle are we concerned with? Well, we just said it was 130 degrees, so it's going to be 130 over 360, part over whole. What percent of arc are we dealing with? So we have 130 degrees over the whole circle of 360. So that's the percent of the circle that we have in this arc. Now what that percent is being applied to the, well, we're talking about arc length, so we need to know the length around the circle. That's the circumference. That's 2 pi. And the radius, which I put in here and kind of ignored, is 7. Okay, so what do we have? Well, we got 13 and 360. We now kind of want to reduce as we go along. And we do have a fraction in our expression, so you might want to just make everything look like a fraction if you struggle with your fraction, just so you can see how everything lines across. Remember, when we multiply fractions, we multiply straight across the numerator and straight across the denominator. And I'm kind of kept myself a little bit tight here on room, so I'm going to cancel before I finish this problem. Both of these end by 0, so these are both divisible by 10. So 130 divided by 10 is 13, and 360 divided by 10 is 36. That's not all the reduction that we can do, though, because we have an even number in the denominator, and we have a factor of 2 or a multiple of 2 here. Well, so 2 is divisible by 2, and 36, which is even, is also divisible by 2. So 2 divided by 2 is 1, and 36 divided by 2 is 18. And that's all the reduction that we have left to do. So our final answer is going to be keeping this in exact form. It means I'm not going to my calculator and getting some decimal that I just round off. Even if I go to like 5 decimal places, it's still rounded off. We have 7 times 10, which is 70. And we have 7 times 3, I'm doing the 13 separate. 7 times 3 is 21. So 70 and 21 is 91 pi over 18. So it's 91 over 18 pi units. Now, we talked a little bit about in the last video, or a recent video, that when you talk about area, a two-dimensional, filling in a two-dimensional space, then there's going to be units squared. But if we are talking about length, that's just some units. So whether your problem's in centimeters, inches, feet, whatever, it's going to be 91 pi units. And that as a decimal, by the way, happens to be 15.9 units. Well, that's the first of my full example, even though it's got a lot of little examples in it. I got 3 more to go. For our second example, you're going to see that it looks pretty much like the last one. So what I'm going to do is I'm going to step out of the video and about every 4 or 5 seconds reveal these answers, to give you an opportunity to pause the video and, basically quiz yourself to make sure you're getting these right and you understand the concept completely. And if not, you can kind of back up and watch the previous one to make sure you didn't miss anything. And then this example here is a bit more complicated, and we'll get to that in just a second. Now go try these. Hope you got them all right. Next example, we have length of AB is 12.5 or 66. So the length of this arc is 12.566 units. I want to use that to find R. So what I want to find, if that's about the center, is this length. I want to find the radius of the circle. Okay, well, if I'm given arc length, this is the first example like this, right? How do we do it? I don't know. Let the formula tell you how to do it. The length of an arc is equal to the measure of your arc over 360. Again, it's just part over whole, percent of, it's just part over whole, it's just a percent. What percent of the circle are you concerned with? Times, and it's arc length, so we need the circumference around the circle, the distance around the circle, which is going to be, again, 2 pi r. Well, the length is 12.566. Try not to have my 5 look like an S. The measure of the arc. Well, I had to throw an inscribed angle in here somewhere, since I put the definition in the video. So if this inscribed angle is 60 degrees, then the measure of this arc, remember an inscribed angle is half of the arc that it basically intersects or encloses. So if this is 60 degrees, then the measure of arc AB is 120. Over 360 times 2 pi r, the variable that we're trying to figure out. Well, I will need a calculator to help me out here at some point, but I do know that 12 and 360, again, are both ending in 0, so both of those numbers are divisible by 10. And then 12 and 36, well, both of these have a common divisor, it's 12. 12 divided by 12 is 1, and 36 divided by 12 is 2, so I can reduce this fraction some more. So I'm going to go ahead and cross that out and put this a 1, and there are 3, 36 divided by 12 is equal to 3. So this big old fraction reduces simply down to 1/3. So let me clean this up a little bit, and we have 12.566 is equal to 2 pi over 3 times r, or 2 pi r over 3. I can make one big fraction and have that way as well. Now, to get rid of this 2 pi over 3, to get rid of, and I wrote this kind of like on purpose, if you have a fractional coefficient, you can get that away from the variable you're trying to solve for by multiplying both sides of the equation by its reciprocal. So we're going to multiply both sides by 3 over 2 pi. And I can do this side in my head. The reason why we're flipping the fraction, of course, is because we have a division of 3, and if I multiply by 3, that multiplication is the inverse math operation. So the 3's are going to cancel, and of course the same thing here. We have a multiplication of 2 pi with it being in the numerator, and here we have a division of 2 pi, and that of course cancels each other out. So we just end up with the radius, which is what we're looking for. And now I do need some calculator help. 3 divided by 2 pi times 12.566 is equal to 6.005. And that is the end of my second example. Ooh, Remote's in my pocket. Just realized in my notes that I hit 577 with my calculator, so this is not right. The radius is actually 5.9998. So we're just going to round that off to approximately, since it's pretty darn close, 6. There was a reason that I had my my decimal here rounded off to the nearest tenths, hundredths, thousandths, because I wanted to come up to a nice, very close to a nice even round whole number as my radius. So anyway, there's the final answer there. Now let's get to our last example. For our last example, which I'm going to get started for you and then let you finish like I did in the middle of the video. We have the measure of arc AD is 50 degrees, and we want to find the length of ADB, which we could also call the arc of ACB. So I want to find the length of from A over to C. Okay? So, or excuse me, over to B. Well, if I'm going to work out this arc length formula, I need to know, remember that's at the measure of that arc in degrees over 360. I have to know the number of degrees of this arc. Well, we're going to, I'm going to verbally just tell you that AC and BD, these are both diameters. So when you learn that this arc over here is 50 degrees, and that means that this central angle is also going to be 50 degrees, and if you remember way back in geometry, when you have two lines intersect, the angles that are opposite each other are going to be congruent. So if this is 50 degrees, this is 50 degrees. And let me just pause this for a quick second. Lost some of my light, so brighten it up a little bit. Okay, so again, I need to know what this entire arc is. Well, if these two these two segments are both diagonals and these are vertical angles and they're congruent, then these two angles must also be congruent because they're vertical angles. So I have to find the measure of arc DC, or the measure of angle, let's call it DOC, so I can add those three parts up and get my entire arc. Well, let's see here. This is a circle. I don't know how many degrees this is or this is, so we've got 360. The full rotation of a circle is equal to, well, just 2 times 50 plus 2 times this unknown value of x. So we have 360 is equal to 100, which is plus 2x. We're going to subtract both sides by 100. And get 260 degrees is equal to 2x. We're going to divide both sides by 2. And get that x is equal to 130 degrees. So, getting back to my original problem, the measure of arc ADB is equal to, let's see here, we have 50 and 50 is 100, plus that an additional 130 that we just found, so this is 230 degrees. And now we're back to the third example in my video of helping you find, or maybe it's the fourth, I forget, but helping you find the length of an arc. So, the length of arc ADB is equal to, well, let's let you figure that out. Remember, it's the percent of the overall circumference. It's the measure of your arc over 360 times 2 pi r. And I'll reveal this in small steps to make sure that you can follow it if you're still struggling. There you go. I'm Mr. True. Bang! Go do your homework.